I do not necessarily want you to copy down unless you're just dying to copy. So I'm going to show you what I want you to copy down, what I want you to copy down. Anything extra you add on this side to help you remember, that's great. But I'll show you what the bare minimum is you need to copy. Okay, so there is a reason why we have so much water, why so much water is able to exist on our planet. There's a reason why it's so important. And there are properties of water, chemical and physical properties we talked about before, that is unique to water. So we're going to be talking about that and why it's so important to us and the things that it can do to help us. So water, we know, doesn't smell like anything, doesn't really taste like anything. In its pure form, it's transparent, which means we can see through it. And then in most lights, it has a bluish tinge in large quantities. We know it covers about 3/4 of the Earth's surface. We know that already. And it makes up most of our bodies as well. 60% of our bodies is water. 92% of our blood is water. So our blood is mostly water with stuff floating around in it. And of course, without water, every living thing on Earth would die. There's nothing living on Earth that can survive without water. All right, so what I want you to do, prepare for your notebook foldable. You're going to cut out your foldable. The sides are where the tabs are. The vertical little column things, that's where the tabs are. You're going to glue. And then the rest of it, you're going to cut around it, and you're also going to cut the little squigglies in the middle so that it makes flaps. By the way, in case you didn't read the tutoring form, for those of you that were staying for tutoring, plan on taking tutoring, it doesn't go to 4:45 anymore, it goes to 4:30. So if you ever ride, just go pick up from tutoring starting next week, make sure they keep you up on time. Well, you're going side by side, basically. Not that much to shoot. So you take my video. So get pencil head up to the table up there and just. Anything you don't finish, you finish in, I said get a pencil, dude. You can finish it, next year you can finish it now. All right. So when you cut out your templates, you're going to glue them in side by side on the same page. You have plenty of room to do it. And then on each one of the tabs, you're going to put each of these labels, starting with polarity. So you have polarity, universal solvent, high surface tension, cohesion, adhesion, high specific heat, high heat of vaporization, and density. You go ahead and glue them in because where you're going to be writing at is underneath the tabs. There you go. So each should have two. Everybody should have two. Yeah. So if you don't have two tabs, go get another paper. Everybody should have a sheet of paper. Yeah, I hope so. If you haven't cut up the flaps yet, that's okay, just go ahead and glue what you got in, you can always cut those out later.
those go on top of tabs?
Yep. All right, for this part, I want you to listen, and then I'll show you what to write. So we're talking about a property called polarity. Polarity is when a molecule, which is two or more elements combined, has an electric charge. Not like an electricity that you can see, but it has an electric charge that you can measure. Has anybody ever seen the clocks, little digital clocks that run off of water? They have them at Walmart for like $10. They're like this big, it's like a cube, and you fill it with water, and that's your battery. And that's because the polar molecules of water have a slight electric charge that's enough to power a clock. So your first tab should say polarity. When you have two hydrogen atoms and one oxygen atom combined, and that's H2O, we know that, they give an electrical charge. And that's because the oxygen atom is slightly negative and the hydrogen atoms are slightly positive. So each one of the molecules has a positive end and a negative end, just like a little bar magnet. So what I want you to write is not all of that, so that's too much. Underneath the polarity tab, you're going to write when a molecule has an electric charge. The great thing about this is that when you have an electrically charged molecule, it likes to attract other electrically charged molecules. That's why water can join together instead of staying separated like oil and water. Oil is not a polar molecule, so it does not join with water well. If you didn't get all of this, that's okay. I'll be putting them back up in just a second. No worries. Another thing, and we've already talked about this when we talked about solubility back in our chemistry unit, water is what's known as the universal solvent. So that should be on the front of your second tab, universal solvent. So because these water molecules are polar, because they have electric charge, and they like to stick to other molecules that have electric charges or are also polar, they're able to dissolve a lot of stuff. So all these charges and all these molecules sticking together cause these homogeneous solutions because they distribute evenly. No, pick your head up. Thank you. And it's called the universal solvent because water dissolves more substances than any other liquid on the planet. And why it's important, why we're studying in the hydrosphere unit and not the chemistry unit only, is because when we talk about water being important to life on Earth, you need to think about how things are moved around the Earth. A lot of the forces that move stuff around the Earth is water. Nutrients, minerals, chemicals, they all dissolve in water, and then water moves and carries it to where it needs to be. So it carries it to plants, it carries it to animals, it gets in the earth where it needs to be. So that solubility is very important. So under universal solvent, water dissolves substances more than any other liquid. And it's important because it dissolves and carries mainly minerals and nutrients. Think about plants. They can't chew up a vitamin. They have to get their minerals and nutrients somehow, and that's through them being dissolved in water and the water being absorbed into the roots. If nutrients were not able to be dissolved in the water, plants would not get the nutrients and then they would die. And eventually we would die because without the nutrients that are in plants, we don't get enough of the nutrients we need. And then the second finish copying. your third tab will be about surface tension. And we talked a little bit about surface tension. Think way back to the beginning of the school year when we did our scientific method lab with the drops on the penny. We talked a little bit about surface tension then. Water has a high surface tension, higher than a lot of other liquids on the planet. So that's what your next tab should be, high surface tension. When you hear the word tension, what do you think of? Stiff, okay, what else? If your rope is under a lot of tension, what does that mean? It's pulled. Maybe tight. It's the same thing with water, except we're not the ones making it stiff or tight or pulled. That polarity that bonds the water molecules together creates this tension along the surface of the water. And it's something we don't really notice because we have such a large mass that we break that tension very easily. But through a process called cohesion, where water molecules stick to water molecules, little stuff, like I call these, I don't know what I've heard them called water hoppers, we call them water skeeters. They're able to actually sit on the surface of the water and walk on the surface of the water without falling in. And that's what this coin is also doing, it's sitting on the surface of the water. That who could do that? Not likely at all. We have too much mass. Oh, well, we're going to do it with paperclip. So what I want you to do is, if you have a cup, you need to go fill it up the sink about 2/3 full of water. The rest of you can go ahead and copy this down. This is what you'll put under the high surface tension tab. When you take your cup back to your desk, don't do anything until I tell you. And don't turn it up too high, it'll spike back up. Water and we'll sit down, that'd be perfect. Stop. Yeah. get it to float on the surface of the water.
Is it possible before
It's possible. People have done it. If you don't get it, just leave the paper clip in there. That's fine. Not yet. Uh-huh. Nope. Just as is. One paper clip. I wouldn't drop it.
Oh, I did it.
Set it in there.
My hands are too big for this. I did it.
Awesome.
Ah. Come on. One,
All right. If you had steady enough hands and set it down just right with the right amount of force, it can float on the surface. The surface tension keeps it floating. If you manage to, I think y'all's group's the only one, tap it with the tip of a pencil gently. Right? You broke the surface tension. So for those of you who weren't able to do it, like I can't do it, I've tried 100 times and I've never been able to do it. What I want you to do is take your small paper towel, set it down first, like this, and then carefully set your, no, that's why you got two paper clips. Set your paper clip on top of paper towel. Now, when you put your paper towel piece in first and then gently set your paper clip on top, it's going to float, of course. All right, now watch me carefully. Look up the screen. When you have it floating on your paper towel, you're going to gently push the paper towel so that it sinks, and then your paper clip stays floating. The reason why you were not able to get the paper clip to float without the paper towel, most of y'all, is because you used too much force or it was at a wrong angle. It's very hard to get it to float by itself. However, if you start off steady and then move your support, which was your paper towel, you're now sitting on the surface of the water. Once it is floating on the surface, tap it with a pencil gently to break the surface tension. Not one of these, but we'll do something else. So, don't stab it. So just pushing it gently, not the cup, the paper clip. Not tap the cup, tap the paper clip. So the reason why, listen, the reason why the paper clip floated was not because it's less dense. Remember we talked about density, and if it's less dense, it floats? The reason why the paper clip floated was not because of density, but because of surface tension. Because when we broke the surface tension, it sank like a rock. It's more dense than the water. But because of those molecules holding together at the surface, you're able to really float light things on it until the surface tension breaks. All right. Don't put the cups up or anything. We'll need them for one more thing. Yeah. So surface tension is also important. Not surface tension. Capillary action is important to plants. Anybody heard of capillary action?
No.
Y'all know what capillaries are?
No.
They're like, your capillaries are like teeny tiny blood vessels. They draw up the fluid around, like the ends of your fingers, the tips of your skin. They draw stuff up into it to enter into your bloodstream. Same thing happens with water, because our blood is 92% water. We already did that. There is something called capillary action. Where'd that really good slide go? Nope, right here. So capillary action is when the water molecules, the polarity of them causes to stick together, stick to each other so well that when one molecule travels, it tries to bring others with it. So what I want you to do to see this in action, and y'all probably gonna be less wowed by this one, is to take your longer paper towel and you're gonna dip the end of it in water, and then you're gonna hold it, and you're gonna observe the water molecules pulling each other up the paper towel. And then we're gonna talk about some. Keep it in there. Keep it in there. Yeah, because you're working like 2 and 2.
I still got this going. Question.
It is, it's just going slowly.
Okay. It started off.
Because you just hold in a whole lot of water and expose it one time, and now if you just hold it, they're moving slower through the water that's already there.
Are they running?
That's how I be like.
So this is a process that you can use in crime scene investigation. What they do, and they have a complicated system to do it now, but one way you could do it, especially before we had all these fancy machines, and you're like, okay, it was made in blue ink, but which pen was it? I have 3 suspects. They all have blue pens, but they're different brands. How do I know which brand made it? So what you do is you take a piece of special paper and you draw a line on it with the suspect's pens. You leave it dipped in the water just like you did until the water rises up past that ink spot. Once the water hits that ink spot, it'll separate into different colors, different shades. Every manufacturer makes a unique shade of blue. Even though they look similar, what they put in it will be a different formula. So whenever they separate, the colors separate, it'll be a unique pattern for each type of pen. This is called liquid chromatography. So you'd be able to say, all right, this brand of ink pen, that suspect, you're guilty. So we use capillary action in forensic science too. This is also the same thing. Okay, I might be showing my age. But have y'all ever seen the lamps or lanterns that have like the cloth wick down in the oil and you light it with the lighter at the top? It's capillary action that's causing that alcohol or that kerosene or whatever ignition fluid you have draw up into that string and cause it to keep fueling the fire. All right, y'all can set that stuff to the side. I don't want you to throw away the cups or paper clips, so just set that stuff to the side because I want to reuse it. That's okay. All right, after high surface tension, your next tab, which would be the last tab on your first cutout, it should be cohesion. Think of cohesion. The word co means like together, so if you cooperate, you work together. Cohesion's where water molecules stick to water molecules. And this is why when you made those drops on a penny, they made bubbly drops instead of just spreading everywhere. They like to stick together as much as possible. The second, or it'd be the first tab on your second cutout, will be adhesion. This is when water molecules stick to other polar molecules. Cohesion, water molecules stick together. Adhesion, water sticks to other polar substances. So let me show you what I want you to write down. Cohesion is why we're able to have surface tension. So this one, molecules stick together easily on surface, that's your high surface tension. And then at the bottom, water molecules stick to other water molecules. This is how water drops are formed.
You know what? I was just playing with you.
Alright, so to talk about cohesion and polarity, I've just decided this like right now. We're going to take the droppers and I want you to put let's do 5 decent sized drops on one of your desks. Not too close together, not too far apart. And notice how they form drops instead of just spread it out flat all over your desk. Make them nice round drops, nice thick round drops. Make some good, nice thick round drops. Yeah, like that. Make about 5 of those. Once you have 5 drops of water, there you go. I want you to use your straw and gently see if you can blow all those drops together into one mega drop. You know what a drop is? Okay, that's a big old drop. Use your drop.
Well, it's in the thing, but it's not, it doesn't look like a round drop.
So, so even if it's not perfect, you should notice those 5 drops are now going together. They're not still separated sitting next to each other. You can blow them so that they stick together. This is the polarity and cohesion. Next time y'all at a restaurant and you're doing this, you can blame your son for it.
I always end up putting my finger in the straw and putting. I did it.
I should put the paper in the straws at my kids.
I should have with that.
You see them sticking together? So those water droplets stick together, combining, that is polarity. Those are water molecules attracting each other, so it's cohesion. The fact that it's sitting on your desk and not being blown way off your desk when you blow on it, that is adhesion. It's able to stick to your desk a little bit. Otherwise, when you blow on it, it goes shooting off your desk. If you ever try to have a drop of something like mercury and you try to blow it off your desk, it wouldn't take much. Mercury does not have adhesion when it comes to things like desk materials. It only has cohesion. Alright, so does everybody have these notes? Can I move up to adhesion? Alright, so adhesions when water molecules stick to other water molecules. I'm sorry, sticks to other polar molecules. That's not water. So this is why if you've ever seen water drops on a leaf, they may even be almost like hanging off the side of the leaf, but not quite dropping. That's because there's adhesion. The water molecules are sticking to the leaf molecules. They're both polar, so they're sticking together. At a certain point, the water will become too heavy and it'll eventually drop. But for a while, it will still stick to the leaf because of adhesion. Same thing as if you have adhesive tape, you have stick tape.
Teachers, please excuse the announcement. I need the following students to the office, and this is a long list, so please just bear with me. 6th grade, I need Alonzo Elias, Selena Morrison, Diego Romero, Monteith McDuffie, Deshaya Lucas, Nicholas Farabee, Paulo Maldonado, Gabriela Baeza, Kelly Mesa Herrera, Alicia Perez, Jessica Chavez, Caleb Torrance, Cameron Daniel, Jaden Lavender, Sadeja Cooper, and Janiyah Moore. Also from 6th grade, I need Senya Burns, Nicholas Blyden, Jaden Moore, Austin Adenery, Jaden Winston, Jasmine Klein, Damani James, and Cheyenne Martinez. 7th grade, and please send these students to the media center. I'm sorry. 7th grade, I need Landon Kirkpatrick, Austin Thomas, Jordan Peace, Joshua Morrison, Laney Lanier, Jerry Rivera, Kennedy Crockett, Alicia Curtis, Janae Duvall, Catalina Cheek, Karen Silva, Elijah Johnson, Berenice Gaspar, Victor Aguilar, Alejandro Garcia, Francisco Pedro Perez, Kaylee Ann Quinones, Liam Sauer, Caleb Morgan, Hajarian Di Dalton, Sarah Escobar, and Sanaya Taylor. 8th grade teachers, please send Dawson Griffin, Victor Vicente, Nicole Coppin Feliciano, Noah LaFleur, Brittany Childress, Jaden Harrington, Kiara Lewis, Destiny Wallace, Santiago Diaz, Julie Gonzalez, David Velasco, and Devin Bundy. Please report to the media center.
David, take your stuff. And take your makeup work. It's in the folder.
What about Autumn?
Hold on. All right, let's have a seat. We're still working. All right, so the next property of water. Brian, sit down, please. Is specific heat. That's what I want you to write on your next tab. Specific heat. This is not something we've talked a lot about this year. But it's something that I wouldn't be surprised would be on a test, benchmark EOG-ish type test. Basically, this is how much heat it takes for 1 gram of a substance, could be water, could be something else. How much heat it takes 1 gram of substance to change its temperature by 1 degree Celsius. So how much energy does it take? Water, out of all the liquids on the planet, has the highest specific heat capacity. So it takes a lot of energy compared to other liquids to raise its temperature 1 degree Celsius. Which is good because if it had a low specific heat, it'd evaporate immediately and we'd have no liquid water. The amount of energy it takes for water to change 1 degree Celsius, 1 gram of water, 1 degree Celsius, either up or down, is 1 calorie or 4.184 joules. Takes a long time to heat, long time to cool. Sand, if you're at the beach, sand changes heat a lot faster than water. That's why it can be a hot day and you run out on the beach and you burn your feet up. You're hot stepping all the way to water because that sand is hot. But you get to the water and it's freezing cold. Sand can get hotter and get cooler faster than water can. The reason why we need good specific heat with water, it affects our climate. Water is at a good temperature so that when it changes just that 1 degree Celsius, they're talking about climate change and global warming, that makes a big difference in our climate. So water is cooler longer so that we don't overheat. It helps keep our climate cooler. If you are living near the coast or you've been on vacation, on cool summer days, that breeze, you don't feel as hot when you're right next to the beach because you get that sea breeze, that cooler water, the wind blows that cooler water and gives you that cooler air when it gets to you. Specific heat capacity also affects precipitation. So if you have water evaporating like crazy, you're going to get more condensation, you're going to get more precipitation. What I want you to write down for specific heat amount of heat 1 gram of substance must absorb to raise its temp by 1 degree Celsius. You need to know that water has the highest specific heat of all liquids. And while you're writing, go ahead and put your next label as heat of vaporization. Now, the heat of vaporization is the amount of energy it takes to change 1 gram of liquid into a gas. It's very similar to specific heat capacity, but they're talking more specifically, like how much energy it takes to make that change from a liquid to a gas. Again, water has a high heat of vaporization point, which is why our water doesn't immediately vaporize back into the air as soon as it hits the earth. Or why we don't have precipitation at all, because it would never form a liquid, it would always stay gas. And then your last tab is density. And we've talked enough about density that we're not going to spend much more time about it. We measure all density levels against the standard, and the standard is water. So for density, you're going to put 1 gram per cubic centimeter, which is something that you may not remember, but something we learned back in the chemistry unit. The density of water is 1 gram per cubic centimeter. And water is unique amongst all other substances that turn solid, in that instead of becoming more contracted, water actually expands as it cools and becomes less dense. That's why if you've ever put like a water bottle in the freezer, cool it down, and you forgot about it, and you come back and your cap might be busted off or your bottle might be busted, and that's because the water has expanded when it turned into a solid, and that's why ice floats. Even though it's still H2O, it just changed state to matter. Water is unique. When it changes state to a solid, it becomes less dense. So we have ice that floats. We'll have to pick up the last bit of this. There's only one more thing we need to write down once we come back for connections. Please make sure all supplies make their way back to the back counter. Straws, paper towels, those can go in the trash, but droppers, paper clips, cups, I do want to keep.